Hi everyone, I'm Hong Jia Heng and welcome to our first session of machine learning workshop. It's called Head Start Machine Learning. So in this session, we are going to introduce you the basic concept of machine learning and kindly drop some question if you have any problem with the presentation and we will try to explain to you. So I'll pass to Jinping.
All right, thanks, Jia Heng. So my name is Liu Junbin, and I'm in my year 2 studies in computer science and majoring in software engineering. So why not let Jia Heng to have some like a longer explanation, a longer self-introduction.
Yeah, so I'm a second year information system student, also from FSKTM. And so basically in this session, what we are going to learn about is a little bit more on theory. And after the theory part, we'll move on to the hands-on coding part. So if you think about, coding, I didn't know about the programming language. Okay, don't worry. So we purposely do so. We want you to get hands-on with the code first. Then after our second session, we'll introduce you more about the programming language and the libraries to use for ML. So don't worry about it. So later, just follow along and try to ask questions whenever you have any problem. So
Okay,
I think, we can start now, and I'll pass to Jinping.
All right. So let's get started. So I believe that you guys have taken your attendance. So let's skip this. So essentially, what we will learn in this workshop is basically we'll go through the first, as what Jia Heng said just now, the first section would be more on the theory side, and the second section would be the coding and hands-on part. So in the theory part, we are going to learn more about ML, like introduction to ML, what is ML and what are the types of ML, types of algorithm that we have. And secondly, we will dive into like a linear regression and gradient descent. So gradient descent basically is the optimization algorithm behind linear regression that makes the whole prediction model possible. Thirdly, we'll go into underfitting, overfitting, and data splitting. Three of these are basically about the performance of the model. So in order to improve our model, we would need to understand more about what will affect the performance of the prediction model or the machine learning model, and also learn to how to improve them. So do not hesitate to drop any questions in the chat box if you don't understand maybe about our explanation, the explanation that we have given, or any material that you have seen on the slides. So what is machine learning? Basically, we have two of this definition. Of course, understanding the definition of machine learning doesn't matter much in understanding machine learning as a whole, but it is good if you understand the literal meaning of machine learning. So you might have heard about like a few terms like artificial intelligence, machine learning, deep learning. So some people will use them interchangeably, but to be accurate, three of these terms are not the same, and they are not jargons. Actually, they can be easily distinguished through this this illustration here. As you can see, AI is an idea. Basically, AI is making the machine intelligent enough to learn and perform their tasks like without hard code. And machine learning is one of the methods to achieve AI. So basically, ML is like the implementation of AI, and DL in turns is the implementation for machine learning. So it is achieved by using artificial neural networks. So we know that we have some traditional way of writing code. So why not we just use those traditional way, those hard-coded manner to solve problems instead of diving into and study ML. So I'm not sure if you have seen this game here. This is AlphaGo. Okay. So essentially, AlphaGo is a board with white and black stones on it. So as you can see, you can have different positions right here that you can place the stones. So if you are going to have a model to play this game, it will take forever to run because it has like 2.08 times 10 to the power of 170 positions to place them. It's not like tic-tac-toe. Tic-tac-toe, you only have like 9 positions to place maybe your crosses or your ticks. So it is terribly slow if you run it on a traditional program, maybe using some of those game algorithms like Minimax or some sort of those algorithms. So that's why we have we would need to apply machine learning in this application, which is one of the machine learning type is reinforcement learning. So if you're interested, you might have to look into the documentary for AlphaGo. So essentially, AlphaGo plays against a international player, a Go player, and it managed to win the player. The player is Lee Sedol, so maybe you can look it up here. Like we just did a very simple comparison between traditional programming versus the machine learning approach. So let's go into a more like a live example into why do we need to apply machine learning. So as you can see in this traditional programming approach, let's talk about the real estate leasing agent. So it's like basically the real estate agent would need to maybe predict the price for one real estate and some sort of stuff. So if we are using the traditional programming approach, we would need a human expert to run this whole process. So essentially, you have the size of the house as the input, and when you get into the human expert will receive this input, and they will need to they will need to label each of those data by using those defined rules. So this defined rules is actually defined by human as well, and they will need to like look through each of those input and think what should be the price, the reasonable price for those real estate. So it will take a lot of time and human resources because you need to hire someone to do it, and also it will take time because humans have their own limitations and they would need to look through the data slowly in order to make a more accurate prediction. Although they are trying their best to have an accurate prediction, but sometimes it just involves some emotional issues and it might run off as well. So in the machine learning approach, we are using, you can see in this diagram here, we have no human intervention in the whole process. So essentially, we have the input, and we are going to pass it into the algorithm, and the algorithm will have an hypothesis, which is called the H here is a model hypothesis, and also simply called the model. So this it will estimate the price based on like the input pattern of the X here. So essentially, if there is maybe like a fluctuation in the price in the real estate market, so probably they can detect those changes automatically without any human like reminding the algorithm or reminding that person. So it can adapt to those changes dynamically, so that we do not need to design do the job over and over again. So you can see here that we are doing a side-to-side comparison. So basically the huge the largest difference is that we are using human expert here in the traditional programming approach, and we are using the learning algorithm in the machine learning approach. So both are better. Of course, machine learning approach is better because if the human expert is doing the job, they will need to be informed about the changes in the rules. So if like I said just now, if there is a fluctuation in the real estate field, real estate market, so they would need to be informed of that, and they would need to change the rules manually. So if we are using the learning algorithm, they could detect those changes dynamically, like through those input, or maybe they will see that the newest input is different from the previous ones, so they can do those adjustments automatically and output a very accurate price. So types of machine learning. Basically, in the machine learning is a broad field. It has it's a very broad field, and but generally it can be separated into two types of learning. The first one would be supervised learning, and the second one will be unsupervised learning. We will dive deep into what supervised means here, and also we'll see what unsupervised means instead. But for now, you just have to take in this structure here so that you know what is the breakdown of machine learning. So in supervised learning, we'll have regression and we have classification. The same thing, we will get into regression and classification really quick. And also unsupervised learning would be, we have clustering and also dimensionality reduction. So in supervised learning, what's the difference between supervised learning and unsupervised learning? So in supervised learning, basically the model is given a labeled data. What do we mean by labeled data? Labeled data is data that has an expected output or the target output y here. So essentially in supervised learning, you will have this y, but in unsupervised learning, you will not have this y. Instead, you have only all those input data, like the x here. The x is the input data. So basically, the main difference is between the data that we get to train the model. Essentially, supervised learning is the labeled data, and supervised learning is the unlabeled data. So like we saw in the breakdown just now, so supervised learning has like a very basic algorithm called regression. So in regression, we are predicting a continuous output. Essentially, like for this example, we have the model is predicting the age based on their selfies. So age is like a continuous value. You can have 17, 18, 19. So it is basically like we get all the blue points are the data points that we get, and the red one is actually the prediction line that we draw on it. So basically, this is the linear regression. We are fitting a best fit line across all those data points. Classification, we have the main difference between classification and also the previous one, regression, is that in classification, we are predicting a discrete output. For example, we can have a binary classification, like only 1 or 0 or true or false, or maybe like this in this figure, we are predicting whether, not predicting, we are identifying whether this is a cat or dog. I actually have some problem identifying it, so maybe someone can have their comments in the chat box. Yep. So another example would be like predicting their marital status based on selfies. So marital status would be married or not. It couldn't be anything in between. So it is considered as classification. Although we can have multi-class classification as well, but for the sake of its simplicity, we'll talk about binary classification first. Unsupervised learning. We have another unsupervised learning is, as you can recall, is a model that receive unlabeled data, and they will need to find the pattern inside the data. So one of the most famous algorithm or most basic algorithm would be clustering. So clustering is like grouping those data. Essentially, like we get only these red black dots here, right? And we're going to these data are not they are not labeled, so you couldn't expect like what output it should be. So essentially, this clustering algorithm will find patterns, and they will group those data points together. Another type of unsupervised learning would be dimensionality reduction. So in dimensionality reduction, essentially we are reducing the dimension. like as you can see here, like we have a 3D, three-dimensional plot here. So this illustrates like this y depends on x1 and x2. It depends on two features. So essentially it will form a 3D structure. I mean, this is a 2D plane, but it's still a 3D plot. So what we need to do is we need to reduce this dimension into this form. As you can see, it's like a bird's eye view of this whole data here. So it forms a 2D plot instead of a 3D one. So why do we need dimensional reduction? So dimensionality reduction actually is applied in various scenarios. So one of the most common one is when you are compressing your images. So we need to know like what are the important features in the image in order to compress them, because we would not like to lose some of the details that is important in the image. So basically we need this dimensionality reduction algorithm to know like what should we reduce and what should we remain. So essentially we have two types of this is not two types of algorithm, because actually SVD, the singular vector decomposition, is a implementation in the PCA, which means PCA uses SVD. So essentially SVD is about it involves matrices, and from that matrices it is able to filter out like what is the important feature and what is not. You are able to see like which feature is important, so that you can maybe prioritize them rather than the others. Like the first, maybe it says that the first 10 features is important, so you would most probably use those 10 features if you are going to reduce the dimension. All right, so the next up we will go into linear regression. Before that, Jiaheng, should we have a break and look into the question first?
I think we can move on, because I don't think there is many questions there. There's just one and I replied it. Yeah.
Okay, all right, thank you. So we'll move on into linear regression. So basically we have learned a few algorithms in the previous slides. So we have regression, classification, clustering, dimensionality reduction. But within those four, the most basic one would be regression. And inside regression, we have actually a few types, and one of them is linear regression. So today we'll get into linear regression, which is I would say like a fundamental model in order to understand ML. But it would be quite a difficult one, but we'll try to simplify it in order for you to flatten your learning curve. I mean, yeah. So before diving in, there is a few things that we would like to clarify. The first one is ML is not easy. So you would not be able to grasp everything in these 2 hours, or maybe master the whole linear regression in 2 hours, because it took me weeks to understand as well. But we'll try to simplify and actually summarize what we hope that we know before we started learning linear regression. So that I hope that would flatten your learning curve. And the next thing, we can't make you an expert within these 2 hours. So I mean the remaining time, not the full 2 hours. So rest assured and just try to like jot down anything that you can get from this workshop. And maybe if you are interested to proceed in this learning process, so maybe you can check out for more resources online. So the third thing is we can only teach you the fundamentals to better understand the literature of ML. And there is some heavy maths. I wouldn't say that it's very heavy, but there are maths knowledge that is applied in linear regression. So it's unnecessary to know, but we'll try our best to simplify it so that it makes you understand more. So essentially those maths knowledge is actually, we actually learned it before in our previous education, before we come to university. But I'll try my best to link all these new things to the old knowledge so that you can get it better and faster. So we have a hand-on session later to solidify the concepts. Right, so later we'll be using a lot of matrices. I mean, not a lot, but matrices. So there's a huge tips that you can apply later while you're learning or trying to understand. So is that always check the shape of the matrix. right? So this is what I get, and I mean Jiaheng maybe get this as well. So which is we tend to be very confused with matrices while we are learning this linear regression. So if you are, so this is like a very important tips. So if you can check, if you know this, it might be easier for you to learn matrices and the application of matrices in linear regression. So the first thing that we'll look into is the univariate linear regression. So basically what does univariate means is like we have only one variable or one feature to be precise. So in the real world, we might have a lot of variables that we need to predict on. But for now, it is good to start off with a simple one, which is a linear regression with only data with only one variable, and we'll see how it looks like. So this is a motivating example. Let's say that we have this example right here, the sample data. So in this sample data, we are going to predict the weight in kg based on the exercise minutes, right? So we want to build an algorithm that can predict the total, predict the weight based on the total minutes of exercise per week. So you can see that we have plotted all the data here into a scatter plot. So this is called a scatter plot. All the data is scattered around here. So if I will ask you to, essentially this is linear regression. So in linear regression, I've shown you before, like in linear regression, we are trying to fit the best fit line across all those data points. So maybe you can think about like how do we fit the lines here? What is the important things that we need to know in order to draw the line? Like what is the equation for straight lines? So you can take some time to think about it, or maybe answer it in the chat as well. All right, so I think most of you have the answer in your mind, but if you don't have, then it's okay, because we are all here to learn. So equation of straight line is y equal to mx plus c. So by knowing the gradient m is the gradient of this line, and also the intercept term, we would able to plot, we will be able to draw the line, the best fit line across all this data. I mean, not the best fit line, the line. But in order to know the best fit line, we would have to know what exactly the gradient is in order to have this best fit line, and also the intercept term. So applying this prior knowledge in straight line, maybe linear equation, so we would apply it into our linear regression here. So basically, we are doing this model hypothesis, which is hx. So I think I've mentioned just now with the real estate leasing agent example, that h is actually the hypothesis. So the hypothesis, essentially in this model, this is a supervised learning model. So which means we have a labeled data with x and y. So x is the input and y is the expected output, that the target output that we would like to get, right? So, and then another thing, there's another new term here, which is the hypothesis. So what is the relationship between hypothesis and the x and y? So essentially x is the input. From the input, we would like to train our model to get an output. And that output that we get from the model is actually called the hypothesis. It is a smart guess made by the model. And we'll compare those smart guesses with the actual output in order to know like whether our model is performing well. So we'll get into all these details later, one by one, but this is just like a very rough overview, like what is the difference between hypothesis and also y right here. So by calculating the hypothesis with this equation here, we'll be able to find like what is the best gradient and intercept term here. So you might wonder, how does these two relates to each other? So you can see here, actually, it's like a same equation, like mx is theta 1 x, and theta 0 is actually c, which is the intercept term. So essentially, this is actually like a linear equation. a equation for a straight line, I mean. So yeah, so I hope that actually links with your own knowledge. It's not something completely new to you, but it is, you actually have a prior knowledge on that. Yeah. So for in model hypothesis, this is the equation, and just like what I've mentioned just now, theta 0 and theta 0 is the intercept term, which is the c in the straight line equation, and theta 1 is actually the weight. This is actually the term that we use in in linear regression in order to like refer which theta is what is which. Yeah. So theta 0 and theta 1 is also called the model parameters. Instead of like calling it gradient or intercept term, they are parameters, and they are theta 1 is called the intercept term, and theta 0 is considered the intercept term, and theta 1 is actually the weight, right? So the difference is between the naming of these parameters here. Before we dive into more equations, it is important to know like the notations that we use in those equations. So if you see m in the later slides, you would it is related to the number of training examples. So like in this data we have right here, I think it is truncated, but basically you have like maybe like these 5 rows. So if we only have these 5 rows of data, our m would be 5 because we have only 5 training sets or training examples. And n is the number of features. Since we are learning, as I said just now, this is a univariate linear regression. So n is always 1 in this case, but we also have multivariate, which we will get into later. X is the input features, which is essentially in this case would be the exercise minutes. And y is actually the target value, which is the weight here, in weight in kg. And the parameters are the ones that I said just now, theta 0 and theta 1. And hx is actually the model hypothesis, or the smart guess made by the model. So yeah, we have a huge, let's say that we have a large set of data here. And we know that we are going to calculate the hypothesis for each of these input, like 62.55, 108.005. We are going to fit them into this equation to get the hypothesis. So you might be wondering, like, how do I apply this on top of all this x here? So some of you might think of using a iteration, like a for loop, loop through each of these rows and apply each of these x into this equation to get the hypothesis. But there's an easier way. I mean, not easier way, but also computationally better. Because if you're iterating over all these samples, all these training sets, all these m's, right, m1, m2, m3, it would take a lot of time. So it is better if we can find another solution to compute it faster. So let's put them into matrices. Let's try to revise what is matrices and stuff. Yeah. So in X, we are going to placing all these exercise minutes because X is the input in the previous notation. Okay. So X is the input features, and the input features here we only have one, which is exercise minutes, because it is a univariate linear regression. And Y, we have only one output for each of these training set, which is 95.39, 57.87. So essentially, we fit all of them into a matrix. Essentially, we call it a vector because it is a times 1. It only have one column. Yeah. And theta we have theta 0 and theta 1. So essentially, these are the parameters that we need. And hypothesis would be the things that we need to compute. So what we want to get is actually a vector of hypothesis. So vectors is actually some sort of like a matrix, but it is has a one column here, so call it the vector. So essentially, what we need to get is a hypothesis with a vector of hypothesis. So which is you will see like there is a superscript here. So this actually means like this is actually the m. like which M we are referring to. So M, like I just said just now in the notation, it is the number of training set, but it also can be like which M would be like which training set I'm referring to. So training set in the other words that in layman terms, it's actually the row in this data. So like we are referring to the first row, we are referring to the second row of X, the X in the third row, the X in the second row, and so on and so forth. So essentially X1 would be 62.55 and X2 will be 108.05. That's the meaning of this one superscript here. So you can see the size here as well is M times N. Since our N is 1, so you get 1. There's actually 100 of training sets here. So there's a 100. Yeah, so you have the same number of output, the expected output, 100, and we have only 1 of the Y. And in theta, you have N plus 1. N plus 1 is because we'll go into deep later. What the heck is this theta 0? Like we only have one feature. Why not we just apply like theta 1 here? So we'll get into it later. So essentially, we need to have N plus 1 rows here and 1 column because we have 2 data here and here. And hypothesis will have the same shape as the Y because we are comparing HX with Y. So that's why it has the same dimension right here. So, right, so like I said just now, we would think about like iterate through each rows and apply this X to the equation to get the HX, but it's too slow. I mean, if we were to train this model like in 1,000 iteration, and you're iterating over this 100 data in each iteration, you could imagine like how much time do you need to train the model. So actually, there's a faster way of doing this, and this is I would say, this is quite mind-blowing to me when I first learned vectorization. So vectorization is basically using the concept of matrices to calculate this in one shot, right? So to me, it's quite mind-blowing. I'm not sure what you think about it. So let's get into it now. So in the vectorized version of model hypothesis, so like I said just now, you might think of using for loop. You have the code right here. This is in Python, but no worries. You'll learn it quite later on in the second session. So essentially, without vectorization, without the new method that I said just now, we are going to iterate through each of those and calculate the prediction. But this is very slow. So what vectorization means is that we turn them into a matrix, and we apply some matrix operation on top of those matrices that we created, and we get the same output, but in a much faster speed. Like we can do it in one shot, right? For 100 of those data right there. So it's nothing magic. It's actually just matrices. So before we step into like how do vectorization works, we will need to look into the X first, because there's a problem here. If we were to calculate, okay, so probably it's a good idea if I tell you that the equation is this. It actually follows something. I will show you why the equation should be like this, but for now you just have to accept it temporarily. So I'll explain it later. So for the X prep, we are going to use the X to times the data. It's actually a cross multiplication, cross product. So there's a problem here, because when we look into our previous one, the X has only one column here, right? But if we are able to cross multiply with this data, we actually have N plus 1 here, and we only have N. So you know that, I'm pretty sure that you know that in matrices, when you try to cross multiply, the number of column here should match with the number of rows in order to get like the product. Yeah. So that's a problem right here. We only have M times N. So, but you know that we only have one X. It's a univariate. So how do we, what's the workaround, or how do we work with this? So essentially, we'll add a row, not a row, a column of 1 before the X1. So why we are adding 1 here instead of 0 or 2 or something? Because let's say like what we want to apply, the application, the equation that we would like to apply to each of those rows is theta 0 plus theta 1 x. So if you see here, if you are doing this multiplication, we're at a row, not a row, a column of 1. Let's just focus on the first one right here. So 1, if you are doing the cross multiplication, it would be 1 times theta 0 plus x1 in the first training set times the theta 1. Right, so this one you can actually ignore it because we are using this one actually meaning it actually means the number of which feature are you talking about, like which column. So it's actually we only have univariate, so we are talking about the first one right here. So 1 times theta 0, you get zeta 0, and plus theta 1 times x1 in the first training set. So when 1 times something, you can just ignore the 1, right? So what you will get is actually theta 0 plus theta 1 times the x in the first training set. So it is actually the same for this equation. I mean, it's exactly the same equation, like theta 0 plus theta 1 times x. So in this scenario, we can use vectorization at the same time, and we also solve the issue of having different dimensions. Right, so the result of taking putting in 1 here is because we would like to achieve theta 0 only. Because there is actually you can add an x0 here, but actually x0 x subscript 0, I mean is actually 1, right? So this is x subscript 0. So what we would like to achieve here is that we only want the theta 0 for the first term right here. So that's the reason that we put in 1 in the first row. First column, sorry. So the same applies for the second data set, the third data set, the third training set, I mean. So when we repeat this, we'll get this whole matrices that applies the same formula, hx formula, on top of different x in each training set. So we'll get, in one shot, we'll get the whole thing, like the whole hx, the hx for each of those rows. So rather than iterating over and over again for each row, we would get it in one shot. It saves time and also computation, right? So this is actually the hypothesis of x1, x in the first training set, or in the first row, and this is the x in the second row and the x third row, and so on and so forth, until you achieve x in the m row, which is the last one, right? So because m in the previous notation is actually the number of training examples. Some of you like programming guys, you might think that, okay, so this is one index, but in programming we use 0 index more. So actually for this index thing, it's actually language dependent. So some languages will use 0 and some languages will use 1. So for the sake of simplicity for this presentation here, so we'll start with 1. But it's actually the same thing. Like if you start with 0, you have 100 samples of 100 training set, you'll get 99 here, right? If you use 0. If you use 1, it will get 100. So the vectorized version. So the code will be like this is not the code right here. Okay, I will find that back. All right, so you get hx like this. So in one shot, you actually calculated the hx for the whole entire training set there, that you have like the whole thing. You can do it in one shot instead of repeating the same thing for each row. So, okay, so now we know that we get the hypothesis. So our model can predict that thing already. So how do we know that that prediction is accurate? So there must be something that we need to use to evaluate our model, right? Okay, I think I will need to turn off my camera because I think my video is quite laggy. So I hope that you're okay not looking at me. Yeah. All right, so let's continue. I hope that you did not miss anything important just now, because I did not realize that I'm lagging, right? Right. So in order to evaluate, like, is our model performing well, there must be something, because you couldn't, like, you ask the model to predict something and then you say that, oh, okay, this is the prediction and this is the best one. So that is not the meaning of training, right? Training is like you have to have a performance measure, and then from that performance measure you have to improve the experience. So in order to repeat this process, that learning process, we will need something to evaluate the model. So in this case, we have something called the cost function. So cost function would be j theta equals to 1 over 2m, the summation of the whole thing, and hx. Hx might be familiar with you, is the hypothesis that we said just now, and minus the y, which is the expected output for the whole model, right? And we square it. So this is the equation. It might take time for you to digest this equation, but I'll try to, like, break it into pieces and explain one by one later. So right, so we get the hypothesis. We have all these hypotheses, the black dots. So sorry, the hypothesis is the blue line. So if you have the blue line and the actual data is this black dots, how do we know that our model is performed, our hypothesis is accurate or not? I mean, has a high accuracy. So in order to get that, there's a way of finding it, which is we calculate the distance or the difference from the actual output. The black one is the actual output, the output that we expect to get if our model is 100% accurate, and also the prediction that we get from here. So essentially, our prediction is a straight line, because this is linear regression, and our prediction should be a great straight line. So yeah, so we're calculating this difference. So you might be thinking, why not we just like hx minus y and just done, right? Why do we need to square and all those stuff, right? So basically, this is called the mean squared error. So the mean squared error means that you square the error and then you mean it, like you find the average, right? So basically, the square here, the motivation of the square here is because we would like to eliminate the negative sign. Like you can see right here, if our hx, I mean this one, the one above here, if our hx is smaller than y, we will get a negative value right here. So if we don't square it, we might get a negative value, which we do not want, because cost function will be always positive. So that's the meaning of the square, to eliminate the negative value. So mean squared error is a method, it's one of them. There is another one which is called the mean average error, but we're not going into that deeply. So essentially, for the mean average error, I can say something about the mean squared average error. So we eliminate the negative value with modulus, right? So for this is mean squared error, so we are squaring it. So why this two? I mean, if we are finding the average, we would just divide by the total number of training sets that we have. So why the 2 here? So essentially, the 2 is actually to make our life easier. You might see the reasons later, but for now, I can give you some sneak peek, which is actually regarding calculus, or more precisely, is the differentiation, right? Our goal is to decrease the cost function, because like the difference between the prediction and the actual y actually corresponds to the cost. If you calculate this cost and you get a large value, means that your hypothesis is actually largely deviates with the actual output. So meaning you're far from the expected situation that you would like to get from this model. So so what we need to do is actually minimize it, because by minimizing the cost will have a lower difference, which means our model is quite accurate in that form. Okay. So if we are minimizing the cost function, essentially we'll just substitute this cost function with the previous equation that we have seen here. It's 1 over 2m blah, 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 and square. So you'll see something different right here, which is theta 0 plus beta 1x. So as you can recall, this is actually the hx, the hypothesis that we get, that we learned previously. So we are just substituting everything so that everything seems like substituted, every terms are substituted. Yeah. So after we get this, we are trying to minimize. So as you can see in this graph here, our prediction is far away from the actual data point. So without like calculating with a piece of pen and paper, you might think that, okay, so this cost is actually higher than the previous one. So I mean, not higher than the previous one, it's higher than what we would like to achieve. So if we are trying to minimize, we try to minimize the cost function, and we do it repeatedly, eventually we'll get to a position to get into a situation where we can fit the line like nicely through those data points. And from here, by comparing these two graphs, you can see that, okay, so this might be more accurate because it is inside the data, yeah, and it logically it would have a lower cost in this situation rather than this one, right? So this might be or might not be our final the best situation that we can achieve, but this is confirmed better than the previous one. Yeah. So it turns out that the cost function looks like this. So, all right, so we have theta 0 and theta 1. So you will be thinking like, why is it 3D instead of 2D? So you'll know that we have theta 0 and theta 1, which means we have two variables here. Although this is a univariate linear regression, but we are trying to find the optimum theta 0 and theta 1 here. So we are plotting the dependency of theta 0 and theta 1 with the cost. So you'll see that it is actually a 3D plot. So yeah, it's a convex function, and there's a global minima here. So this is the lowest position that we would like to get, because this has the lowest cost in this case, right? So this is like sometimes we should not be too optimistic in this thing, because sometimes we'll get some plots like this. So in cost, there are a lot of minimum. You can see this is the minimum, this is the minimum, and this is also the minimum. But those are actually called the local minimum, which means it's not the minimum in general. It's not the minimum. It's not the overall minimum. So we would like to find like where is the global minima. So global minima here means that the lowest position in the whole plots here. So sometimes when you're doing, right, you might stop in the local minima here. So this is a more less optimistic, a more pessimistic situation here. But for now, we'll just focus on this one, which we only have one global minima. So whenever we go, we just stop at this position right here instead of stopping in other local minima. So we have a convex function. So what can we do if the function is a convex function? We can compute the derivatives. So all right, so before this, I would like to ask some questions, which is you can answer them or not. You can think about it before this. So before this, I'm pretty sure that you have learned about quadratic functions. So in quadratic functions, if I will ask you to find the minimum of the quadratic function, like find the position of the minimum, what would you do on the quadratic function that you get? So probably you can think about it. Right. So yes, so we are going to calculate the derivatives. So which means that in like when we have a 2D quadratic function, right, we are going to find the minimum because we know that the minimum has a gradient of 0, like dy dx equals to 0. So essentially this applies to the same thing here. Instead, maybe you see here that we have a convex function and you might think that, oh, how do we do this? But we're going to focus on maybe only one data, depends on only one data right there. So all right, so we are going to find the minimum. So we know that by looking at this quadratic function, it might be more familiar than you than the convex function. So in order to find the minimum right here, we know that dy dx equal to 0, but in certain cases, we would only know that dy dx is the most minimum in those cases, like in the minimum position. Like here, it might be 0, but like in this position, like when you're moving from A to B, you might not know, like it might not be 0. I mean, because you're calculating the dy dx or the gradient at the A position, right? So you're moving slightly to B, which is the optimum position that you would like to achieve. So we only have to say that, okay, dy dx should be the most minimum when we reach the global minima, right? So essentially, we are calculating the gradient, and we are adjusting the theta, which is the parameter, based on the gradient right here, minus the gradient. So essentially, this is a differentiation term. It means finding the gradient. To be honest, if you did not learn about calculus, it's about like finding the gradient at this point, so that you can like subtract, adjust the data based on that gradient right there. So we'll repeat this over and over again until you reach the global minima, which has a minimum cost here, right? So as you can see, this actually expands the whole iteration. Like all right, so we'll repeat this until theta is slightly approximately 0. As I said just now, dy dx is equal to 0 is the most, like I could say it's a euphoria of like getting the most getting the global minimum. So though I say that you are subtracting the gradient right here, but what is this term? Like you have a alpha right here. So this alpha is actually the learning rate. So this learning rate, as it sounds, it controls how fast the model learns. So in terms of how fast the model learns is actually in mathematical form is actually how much do I subtract from this data right here? How much do I adjust the theta in one time? So let's say that, okay, the gradient is maybe like -15. So if I were to adjust it largely, I could set this to a larger value than 2. I could set this to 3 or 4 or something. So I will be subtracting 4 times the gradient. But if but in this case, if our alpha is too large, it might lead to a situation where it overshoots. Like because you are subtracting the theta too much, so it will just run to the other point and get to the other point because you are adjusting it too much in one time. So what we need to find is the best learning rate for the model. So that's a pretty important thing. Yeah. So we are going to find the alpha, the best alpha that we need. So we're just essentially this is just a trial and error thing. From what I know, it's just a trial and error thing. So you need to find the best alpha so that it is not too small, because too small it will learn too less. I mean, learn too slow, because in this case you're subtracting in lesser than it should be. So it's actually like the learning rate in here in mathematical form is actually how many do you adjust the parameters. So that is a mathematical concept there. So if you're too small, it will be learning too small. If learning too slow, it will adjust it bit by bit, and you'll take a long time to get to the minimum here. And if it's too large, it will overshoot and it never gets to the minimum. So we have talked a lot about adjusting the data. So what does this mean? I mean, it should have a name, right? So yeah, there's a name for it. It's gradient descent algorithm. So in gradient descent, we are repeating this whole process that I said just now. We're adjusting the data with the gradient. Therefore, it's called gradient descent because we are minimizing the data here. I'm not sure. I think it's minimizing the cost using the gradient, right? Because we are not necessarily minimizing the data, because you can see here sometimes it will get to like plus or something. So basically we are just minimizing the cost, the J data right here. But in order to find the in order to adjust the data here, we need to find the gradient for this cost function, right? So every time it will be different because we are changing the data here, and data is used to calculate the hx or the hypothesis, and the hypothesis is used in this gradient function. So the gradient will be different every time, and your data will be different every time. So you can see here the differentiation of this finding the gradient. The equation for the gradient is this one. So you can see we are using hx. So hx is actually theta 0 plus theta 1x, right? So if your theta is different, in that case, your hx will be different. And if your hx is different, the whole gradient will be different every time. So basically, we are adjusting it bit by bit differently every time. So we'll get to the local minimum right here. Okay. So this is the derivatives of the cost function. I said just now, like, why the 2 right there, right? So essentially, it's because of this derivation. So this slide actually shows you how do I get from j data, which is this one right here. This is the j data. And how do we get this to this one right here? Oh, yeah. And you can see there's a difference here, theta 0 and theta 1. This is because, like, in theta 0, we actually minimizing the theta 0, right? Because, you know, in differentiation calculus, it's okay if you don't know, because this is actually nothing. You can still understand the whole concept without knowing the derivation, but it's good to know, like, why this is theta 0 is different and theta 1 is different. So in theta 1, when we are differentiating the cost function with respect to this theta 0, theta 1 will be actually constant in that case, right? Like when we are doing the differentiation. So the theta 1 will be constant in this case, so that we only have theta 0. We're only differentiating theta 0, and same to this case. So actually you have an x0 here, but x0, as I said just now before this, x0 is actually 1, right? X0 is always 1 in this case. This is x0, x subscript 0, sorry, x subscript 0. I don't want to confuse it with the superscript here. The superscript here means the number of training set, like which training set are you meaning, which row do you mean, right? So essentially x0 is always 1. So if there is a 1, we can just ignore it because it doesn't affect the whole equation right here. So you have no x0 right here. So essentially they are, I could say that they are the same thing. Jiahong, correct me if I'm wrong. Because the x0 is 1, so that we can cancel it off. So it just simplifies the whole equation.
Yeah, it's correct. And actually, if you guys are wondering what that looks like a inverted 6, what that means, it is actually called partial derivative, and it is used when our function not only contain one variable. So in normal case, we just have y equal to mx plus c. Then if we want the derivative, it will be dy dx. So we just have one x. Right now, we have two x. One is called x1, one is called x0. So when we have two variables, the derivative is called partial derivative, and we will treat other variable as constant when we are deriving with respect to theta 0, for example. Yeah.
Yeah. So as you can see, in this case we are deriving with respect to theta 0. So in this case, actually, it's quite complicated here, but you can see there is a 2 that we slash off here. So this is the reason why I said there is a 2 in the bottom instead of just divide m, because in logically we should just divide by m, because it's like finding the mean of those squared errors, right? Mean squared errors means finding the mean of those squared errors. So why is this 2 necessary? It's just to make our life easier, because when we differentiate, this 2 power 2 here will actually becomes 2 times the whole term here. So if we can cancel out the 2, we just left with 1 over n. So it might be easier to calculate in this form. Right, so this is calculating the derivatives of the cost function with respect to theta 1. So you might be thinking, okay, so we have theta 0 and theta 1, but you're saying that we are learning the univariate linear regression. So essentially, you are learning the univariate. We only have one feature. So the theta 0 is just actually 1 in front. right? So not to confuse you, we are still in univariate, but just that we add a 1 here, which is x subscript 0, is x and 0 in the bottom. So essentially that's just 1, so it doesn't affect much. So let's get into multivariate regression. So before that, do we have any question for univariate? Oh, I see. I think everything is answered. Yeah. So I think we shall proceed with multivariate. So in multivariate means we have multiple variable, like how it sounds. We have multiple variable, and we don't have only x1, x subscript 1, but we have x subscript 2, x subscript 3. So for this form, we will not go into those example data because it might be quite confusing, but we'll learn about the general form of like how it works and how should we compute, how should we expand our knowledge from univariate into multivariate. So when we can have more than one features, of course, that's the reason for these slides. So as you can see, this sample, we still show you the sample data, but we will not like get into the calculation and stuff. So essentially we have exercise minutes, and before this, we don't have this calorie column. We just have the exercise minutes and weight. So for now, we have added a new feature here. So which means weight actually depends on exercise minutes and calories, and we're going to predict the weight with these two features. So in this case, n is equals to 2. Right. So in general form of x, y, and theta. So all right, I get a little bit laggy here. In general form, x is like what we learned just now. X has only one, like maybe the x subscript 1, x subscript 2, x subscript I mean x1, x1. The one in the bracket is actually the training examples, the training set, like which training set we are referring to. So essentially we only have this column here, right, for the univariate. So in multivariate, we actually expand this whole matrix into instead of vector, we have a matrix of m times n. So n would be the number of features. So in this case, we have 2. So we have two features right here. Right. So all right. So for y, it's the same thing because of course for each of this we only have one expected output, which is 88.47 and so on and so forth. And data, we have more than one because this data actually depends on how many features that we have right here. So if we have n, means we have n plus 1 times 1. Why the n plus 1? Because n plus 1, because we need to add another rows of 1 here. Instead of, because before this x subscript 1, we actually have another x subscript 0 in front. So that's what we need to, that's the x prep, right? Like like what you can see before this, like in vectorization, we actually add this 1 in the front of it. So it's actually x subscript 0. So in this case, we have n plus 1 times 1 because we have another, we have to add another x0, which is 1, and we have a theta 0 in front. And hypothesis, so we are getting the same hypothesis. It's a vector the same size as the y because we are comparing, because when we are trying to minimize the whole thing, we're trying to optimize the whole linear regression, we will need to compare the hx with the x and calculate the cost, right? So like what you learned before this. So by having this hx same with the same shape, so we are going to compare it 1 to 1. So it's like element-wise thing. So it's actually just a matrix subtraction when you do it. So basically that's what we're doing right now. So you can see here x prep of, I think, okay, I mentioned it just now. We are adding 1 to the first column right here. So it's m times n plus 1, so that we can use x prep time cross multiply with the data because we have the same dimension right here. So when we cancel off this n plus 1, we get m times 1. So m times 1 is actually our hypothesis here. So that's the whole point of vectorization, which is we get the hx is m times 1 by just in one shot with vector with matrix cross product, right? So if we multiply n plus 1, just cross off and we get n times 1. So in general form, m training instances and n features. So you can see that this is the hypothesis and the parameters just like before, just that it is larger, the vector is larger, and we have the cost function, which is the j data, and we have the gradient descent, which we repeat the whole thing until we get the minimum cost. Right, so this is the, this is the iteration way of doing it. It's not wrong, it just takes time. So maybe if you are interested, you can get into the vectorized version, but I will not repeat this for now. I will not go into this, because yeah, you can look into it later on your own if you're interested in. So basically, vectorization is just works the same way. It's just like we would like to use matrices to make our computation faster. So it's like when we are squaring it, we'll just do this. When we transpose it and we do a cross multiplication, we'll just get the square. It's the same result as the square. So basically, we are using matrices to optimize our model. So in general form, right? So this is the cost. It's the derivation of the cost that we can get right here for each of these data. So and okay, I'm going back again. So yeah, so you can calculate this whole thing. It's the same thing as the previous one in the univariate, just that for now we have more than one data, more than two data, So we have data 0 and maybe data 1 to n, because we have data 1, data 2, data 3, based on how many features that we have in our data set. So in this case, 2, so we have only data 0, data 1, and data 2. So we need to calculate the derivation for each of them. Right, so there's a j, and j is for j1 to n. So model hypothesis vectorized version. This is an optional proof. So you can look into it. This is a completely optional. So you can see that it's m times 1, and yeah, that's how it works. So you can just, when you do the cross multiplication, you just get m times this one, and the center is cross off. This is how the cross product works. So the last thing that we're going to learn is overfitting and underfitting, and also the data splitting. So for overfitting and underfitting is actually an issue when we train our model. So in some cases, it might fit perfectly. Like this is underfit because you can see that the data shouldn't be a straight line in this case. Although we are learning linear regression, but sometimes it might not be a straight line. The most best line should not be a straight line, but it just underfit. So it is underfitting the data means it doesn't generalize the real world data. That does not fit the training set. Sorry, it does not fit the training set well. So it just it doesn't train well. So there's another thing which is under overfitting. So overfitting, you can see that it's generalizing the data too well. It fits the data too well, but it doesn't generalize the real world data. Like if we have a real world data right here, a new data, so it might not be able to predict it accurately because it's fitting too good. Too good to be true. So in this case, it might not be able to give a very accurate prediction. So another thing is a good fit. So a good fit would be it generalizes the data. You can see that it doesn't fit everyone, but it just pass through all the lines, and we can get a nice prediction right here. So this is what we would like to achieve, but in most cases, we'll get into this trouble as well, underfitting and overfitting. So in data splitting, we are splitting essentially, you can split it into two sets, but three sets is the best. So what we name those three sets is as the first one is training set. This is the first set, and cross validation, and also the test sets. So the objective of data splitting is to make sure that because when you are fitting all the data into the model, you will not be able to test whether the model performs well with like new data, because all the data are not new to them. You already train it with those data, right? So essentially of splitting those data is that we have the same set of data, but we use them differently. Like for the first set, it will be training. So we will use it for training purposes. And the second one would be cross-validation. And the third one would be testing the model. So it is to make sure that the model does not know the test set so that we can test them after we train the model. Right, so that's the whole point of doing data splitting. So I think that's all for my session. So the next one will be I'll pass it to Jiaheng to do the coding session. Right.
Yeah.
Thank you.
All right. So before that, is there any question on the presentation just now? Yeah. So we are going to have a 5 minutes break, even though the time is already delayed for 5 minutes. But never mind. We'll keep the 5 minutes break right now because I think that there's too much information going on right now. So okay. So I'll share my screen and let's take a 5-minute break. Oh, sorry. So I think I'll just reply the question right here. Okay, so how to handle an overfitting? So actually overfitting for linear regression is not possible because we are just predicting a straight line. And if we have two features, we are fitting a plane. So everything is just linear. So it's not possible in linear regression. But when we have more complex model that can fit, curvy data, then it will happen, the overfitting will happen. Okay, so how to handle overfitting is a very big problem in machine learning, and there's many ways, and we will cover it in session 3. So yeah, stay tuned. Then for what is the difference between cross-validation and test set? So as we can see, test set is a training set, a set of data to test our model performance. So it's not used when we are training the data. So if we want to ship our model out, so we have to have a test set to know that, oh, so this is how well our model perform. And cross-validation set is the set of data that used to choose the best model among several models that have different hyperparameter. So for example, just now we say that the learning rate alpha have to be choose. So right now, if I have several choice of learning rate alpha, and yeah, I train different model, and finally I'll test it on cross-validation set to see, okay, whether which model perform the best. So yeah, that's the point of cross-validation set. It is to help to choose the hyperparameter. So hyperparameter is the parameter that, for example, number of iteration in gradient descent is also a hyperparameter. Yeah. And the learning rate alpha is also called a hyperparameter. This is the thing that we need to choose before training our model. Hope you understand it. Yeah.
But for the hyperparameter, it's used in like pre-trained model, right? It's not applicable to linear regression.
Yeah, actually all this argument that we have to set to the function, all this variable that we give externally is called hyperparameter that we don't learn during the gradient descent step. Yeah, meanwhile, remember to sign in your attendance right there. So we have 1 minute left. Yeah, so time's up. So I hope everybody is back right now. And I need your help to set up your coding environment. And we will use Google Colab for this purpose. And yeah, let me send you the link right here and you can just access it there. Okay. So let me share my another screen. All right, so are you all able to open it? So it should looks like this. So after you open, kindly click this copy to drive so that it copy to your Google Drive and you can save the changes that you have made. So it's just like a template, not a template, yeah, a template, and you make a copy to your Google Drive. All right, so I think we can start right now. So welcome to the coding session, and in here you will build a linear regression model from scratch. So implement all the equations shown just now, and you are going to implement the batch gradient descent. And then, oh yeah, batch gradient descent is called batch gradient descent because we take all the n training example at the same time to do the gradient descent step. So actually there's other variant to gradient descent. Yeah. So yeah, then we are going to apply the linear regression model that we have built on the 1D dataset and also 2D dataset to make prediction. Then we are going to do something called feature scaling. So to scale our data before we start training so that our model learn faster. And then we are going to visualize the prediction of our model. And then we are going to visualize the cost function. And we are going to understand underfitting and overfitting. So yeah, let's start. Before that, kindly click this connect. So this is Google Colab and it is an interactive online Jupyter notebook. So you can just run this by clicking Shift Enter. So it takes some time to connect to the Google server. Yeah, Shift Enter and everything will be run. So for example, right now I type print hello world. Shift Enter. Yeah, so hello world will be out. Okay, so if you want to delete the sound, just click this. All right, so before that, if actually we haven't teach you more about Python, so we are going to use Python, and yeah, kindly just follow, and you will learn more in the next session. And I'll try to explain as clearly as possible during the live coding session. So Numpy is actually the library for matrix multiplication. Yeah, so everything related to cross product, dot product is in this library, and pandas is a library for manage the data better. Is like Excel. Yeah, and then matplotlib, this library is to plot our data. It's used for plotting. And then these two plotly, it is used to plot interactive plot. All right. So yeah, let's go. And first one, I actually pre-written the code and it's used to generate the data set. And we have one data set with one feature right here, and also a data set with two features. So we'll see that later. So don't worry about here. So it's not the point of this workshop for understanding this all. And let's generate the data set, run the function. And here, so we want to load our data set out, and let's call this function generate data set. Okay, so what we need now is to specify we want 1D data set and write 1. And let's set a seed so that every time, so I'm using random initialization there. So if I set a seed to a random initializer, I can get the same value as well. So let's set it to 1. And then x1d, y1d. All right, so we have generate our data here. So we can try to, print it out. So our x1d looks like this. Okay. So y1d. Okay, so it also look like this. And let's see the shape of it. So yeah, we can see that the shape is 100 by 1. So we have 100 trading example and one column, and it is n equal to 1, the one feature. So now let's plot it out for visualization. Now we call the matplotlib object plot.scatter and x1d as the x-axis, y1d, and then plot.show. So we are going to show the plot. All right, so here's the data. And let's add some label to it. So plot x label, I call it exercise means. So the total minute of exercise per week. Plot y label, weight kg. All right, run it again by clicking Shift Enter. So, okay, so now we are going to build a model based on this. And so I think, okay, no, let's move on. So now we are going to visualize the data set with two features. We load it first, x2d, y2d, then generate data set, n equal to 2, and seed equal to 1. And then, so now let's visualize the data. So for 3D plot, it's quite different when we plot in matplotlib. We have to initialize the object first, and then initialize the axis. We have to add a subplot to the main figure, and we have 1, 1, 1. This means that we have one row of figure, one column of plot, and total number of one plot there. And then projection 3D. All right, so then we say ax.scatter. So we are going to plot the scatter plot, x2d. So x2d, yeah, before that, let's visualize the shape again, dot shape. All right, so it is 100 by 2. So let's set it 100 by 2. Let's take the first file to see it clearer. So this is the first 5 x2d, okay? And now when I plot, I want to specify the x-axis and then the y-axis and the z-axis. So x-axis, let's put it as this because we want all the m training example and column 0. Yeah, so it's just like we taking the column 0. Sorry, so we take the column 0, the first column, and then the second column. Right, so here we said about x2d 1 and z is y2d. Yeah, then I think that's all. Plot.show again. And the data is out. Oh, so actually this should be called xs, ys. No. Then I don't think we need to put this right here. All right, so here's the data. Can you follow along? All right, so I'll just continue. So our data set is right here, and we'll solve the 1D data set first, which is we want to fit a straight line to predict the weight based on the exercise mean. So let's use it with do it with the easiest way by using library. So the library is called Scikit-Learn. So everything is being implemented in the library, and we initialize the model, and then we train the data. It's called fit. We fit x1d and y1d. So this fit, it will run all the gradient descent inside. All right, so after it's fit, then let's run this. So we made a prediction using the linear regression model from Scikit-Learn. Yeah, so actually it is that easy in actual case, but right now we are going to learn more about it. So we are going to implement it from scratch. All right. So right here. So actually here, let me explain a little bit about this. We init x, we initialize x that span between minimum of x1d and maximum of x1d. So we initialize this, and then we span 100 real value number there. So it's like here, 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 and here. Then we do the prediction on that using the linear regression model that we have trained, and we plot the prediction with our x and our y. So yeah, here's our prediction. So don't worry about it if you don't understand the code yet, because yeah, we have session to help you on this. Okay, so now we'll start building our linear regression model. So okay, so here what we need to do first is to concatenate a column of 1 to our x so that it can be used when doing vectorization implementation of our hx. Okay, so we want to do this because we want to run it using matrix library so that it can run faster. So let's do this. So let's implement this function. Before you see me write it, you probably can think about it. How do we need to do this? So given x, we have x right here. We want to concatenate 1 to this. So before that, let's initialize 1. All right, let's initialize before that, let's take the m. So we want to know how many training example is here. So we put length x. So it's like the length of x. Okay. How many training example is right there? So m. After that, we put m and 1. So we are going to initialize a matrix, a matrix with shape m by 1. Yeah, and then later we'll concatenate to the x. Okay, so to concatenate it, we do this numpy.c. So it means concatenate and a square bracket. Then I put this one right here, and then our x. So that means I concatenate this to the left of x. All right, so what should we call this? X prep. And return x prep. All right. So to show you about it, so let's see, this is our x1d. Okay, with just one column. Then we use this function concat x0. It will return this. So add a column of 1 to the left of x. Yeah. Okay. So any question until here? So I hope that everybody can follow along, even though you don't familiarize with the code yet, so that you can learn. It's quite a steep learning curve in my opinion for you all, but yeah, let's get through it. All right. So after this, let's implement our model hypothesis. So in a non-vectorized version, it looks like this. So just now we said that it's not only this, because if we have more than one feature, if our n is 100, if we have 100 feature for us, yeah, then this will be 100. And then the vectorized version is going to be generalized well with with whatever n we have. Yeah, so let's do this. So assume that we now have the express here, and we have a data. So the shape of data is this. Shape of data is n plus 1 by 1. Okay, so now we are going to compute the prediction. Let's call this y predict. Okay, y predict. And then we do this numpy dot. Okay, and then we put express here and data here. Then return y predict. Right, so this dot is actually dot product. So when numpy, this function see this kind of shape, because now our shape of x pred is m by n plus 1. So when it see this, it will automatically use the matrix multiplication for us. Okay, so yeah, let's do this. All right, so later we'll try this function because we haven't initialized the data yet. Okay, let's proceed. So our model hypothesis is done. So if you're not sure about this yet, later you can refer to the proof that we are showing in the slide. Okay, and then yeah, let's implement the cost function. Before that, can I challenge you all to implement it without vectorization first? Do you want to try it? So for cost function, non-vectorized version is actually quite easy. So it's like, all right, so I said it cost, and then I have 1 over 2m right here, so 1 over 2 times m, and then I times with all the sum of the difference between the actual value and the predicted value. So let's do this first. So I have y true and y predict. Y true is this y superscript I. Y predict is h of x superscript I. So y predict minus y true. And then we need to apply power 2. So in Python, this double multiplication sign is power. All right. So what we left? We left this m sum over I through m. So actually there's a function in numpy called numpy.sum. We will sum it automatically. All right. So let's return the cost. So this is not a vectorized version of the implementation. Let's run this and let's try this. Compute cost. So assume our y true is y1d, okay? And then y predict is also y1d. So what happens if this is the case? The cost will be 0, right? Oh, what's wrong? Yeah, we don't have the m. So how do we get the m? So m, we can get it from length of y true. Right, so we can also do length of y predict. It's the same. Yeah, let's run it again. Yeah, so the cost is 0. So this is non-vectorized version. So let's do the vectorized version. The cost is equal to 1 over 2 times m, and then times with the y predict minus y true. All right, and then you want to apply this transpose. So in Numpy, the transpose is just dot t. So it will return a transpose of this matrix. All right, then after this, what we want is also a matrix product between these two. So let's do this, numpy dot. All right, and then the second term will be this, y predict. Oh, sorry. The second term will be this. Okay, let's run this. Oh, before that, let's comment out this first. So the cost is also 0, but it has the double column because what is the shape of this numpy array? It's 1 by 1. So we can just apply this function because cost is a real number value. You don't need it to be a matrix. So let's put this numpy.squeeze. So it will squeeze all the shape of it. Yeah, so it will be like this. Right. So both of this is okay. You can do whatever. So let's say I choose this vectorized version because I think that it is faster. Now let's move on to the derivative of the cost function. So why do we need the derivative of the cost function? Because we want to use it for gradient descent to update the data. All right. So this is called nabla. It is gradient. Is a vector contain multiple derivative, and nabla j of theta contain this all. So we want derivative of j of theta with respect to theta 0, then with respect to theta 1, and so on until theta n. So we can know that the shape of the derivative is going to be m plus 1 by 1. All right. Yeah. So what is the inner loops of this derivative? It is this. So if you can recall, then that's very good. If you can't, yeah, that's okay too, because we don't need to memorize it. So, all right, so the vectorized version is this. So it's quite easy. Now let's do this. So we need y predict, h of x is the y predict. And then we need y true is the y. And then we need, what's more? We need what? The x. Okay, so yeah, let's do this. So we call this gradients, grads. And then 1 over m times. So this is going to be a matrix product. This and this. All right, so x prep dot transpose. I want to transpose this. And then let's put it in the numpy dot. And then we want to know the difference of this, y predict and y true, minus y true. Oh, y true. Yeah, let's return the gradient. On this, let's try this, cost gradients. Assume that our y predict right now is y1d, is the y1d that we have just now. Then our y true is also y1d. Then for x prep is x. We haven't do that. So let's use our function concat. This is the function that we returned just now. We want to concat this x1d. Okay, let's run this. Oh, what's wrong? Okay, sorry, m again. So m is going to be the length of y predict. Actually, we can also write this as the y predict dot shape. So this shape is going to return m by 1. Okay, then if we put 0, it will take the m. if we put 1, it will take the n. Yeah, so we can do this also. In case you don't know what I'm saying, so you see y1d dot shape. So this is called a tuple. So it's just like an array, and then I can access the first one of it, which is 100, and then I can access 1, which is 1. So if I put length y1d, I also can get the 100. So it's the same. All right, let's go run this. What's the gradient? Wait, m is not defined again. Oh, because I haven't run this function, sorry. All right, so when our predict value and the actual value is the same, then the difference is 0. And then from this, we can see that all the things we can get is also 0. So the gradient is 0. So yeah, let's see the shape. So the shape is going to be n plus 1 by 1, right? So shape is n plus 1 by 1. All right, so our n now is 1, and n plus 1 will be 2 by 1. So let's see. Dot shape. Yeah, 2 by 1. Yeah, that's correct. All right, so let's move on. I'm not sure that you guys are following or not. So if you think there's any problem, just tell me. I'll help you. I'll help you out. Yeah, before move on, do you guys want to try to implement the non-vectorized version? I think, yeah, we give you 3 minutes to do so, or I just demonstrate it. All right, so I think I can just demonstrate it, okay? So how are we going to do this? So this j is going to be 1 to n. And then right now, I can't compute it in one go. Let's us initialize our gradient first. So it's going to be n plus 1, right? So now I want to take y. Oh no, I want the n, so it's going to be this. Because the shape of y predict will be shape of x predict. Sorry, shape of x pred is m by n plus 1. So when I take this, it will get me n plus 1, so I want to minus 1. So let's initialize the gradient. Oh, I don't need to do so. I can just write n plus 1. And then here, n plus 1. So delete this. And then, yeah, n plus 1 by 1. So here's the shape of the gradient. And let's do this. Gradient 0. So you can think of it as a vector, and then I'm accessing the first entry of it. So I'm going to fill in this 1 over m times numpy dot sum over y predict minus y true. Right, so let's comment out this first. So now I get this with respect to theta 0, and then I want this with respect to 1 to n. So how are we going to specify this? So let's do this. So I want it from 1 and to the final value. So in Python, this is called indexing. So I'm going to access 1 to the final one. All right. If I put 2, if I put 3, then I'm going to access 1 and 2 because it's not include the final value. So if I put 5, I will get 1, 2, 3, 4. So now if I put this, I will just get 1 to whatever the last value is. So yeah, let's do this 1 over m, and then times numpy dot sum. So this is just normal product. This is not matrix product because this is a real value, a single value. But before that, I don't think I can access it right now. I need to do some kind of indexing to get it. But yeah, let's get this first. Let's write this term here. So I'm going to write this y predict minus y. So this is this term. And then now I'm going to get this x subscript j superscript I. So I want this times that. All right, so how to get this? X at, I think we need some kind of for loop for this. Otherwise, we need vectorization. So let's figure it out right here. So the shape, should I do this here? Let's do a for loop, okay? For j in range 1 to n plus 1. All right. So I don't want to do the vectorized version, and I put it as gradient j, and then 1 over m. So I'm going to do this sum xprep. So how do I access it? So the shape of xprep is m by m plus 1. I want to get the m training example. So probably I also need a for loop here. Then in range m. Actually, I think this is unnecessary to do so, but who knows? Let's try this. So this will be I, and this will be j. I row, j column. And then we need to do this one. So grad 10. So here let's initialize it as 0 first. And then, okay, so grad 10. So grad 10 will, sorry, I don't think I should do this here. So I, okay. Finally, I get my entire thing here. What I left is just the grad j 1 over m times my grad 10. Okay. Yeah, let's try this. Let's see if it's going to be the thing that we get just now. Oh no, y is not defined. Oh yeah, y true. Sorry for that. Y true. Yeah, so we get the same thing. So you know what? Vectorize. If we do it vectorize, do the vectorized version is very easy and very intuitive. If you want to do the for loop, yeah, it's hard. We need a lot of indexing. Yeah, so now let's just comment it out. Okay, we'll use this. So this is non-vectorized version. And then this is the vectorized version. Actually, this one, I can also come up with a vectorized version, but I haven't calculated it beforehand. So I need some time to do it. So I decide to just indexing all the way. Okay, let's go. We are pretty slow right here. So now let's move on to gradient descent. All right, so before that, let's recap on something. So from the slide, what we have is the hypothesis, the parameter, the cost function, and the gradient descent. We done hypothesis, we done the cost function, and we haven't done this. And parameter, we later need to initialize it. And then gradient, I've also done it. So let's move on to the gradient descent. Okay. So here is not a non-vectorized version of gradient descent. Then this is the vectorized version. So you can think of it as now all this data is being updated together at once. And this one is just I update theta 0 until theta n one by one. So actually I've started with some starter code here also. All right, so gradient descent, in the formal definition of it, we don't have the number of iteration. And then number of iteration depends on us. And we just say repeat until convergence. It means we repeat it until the function converge. It's like we repeat it until the gradient is near to 0. So as we know, when the cost, so when we reach this point, our gradient will be near to 0 or 0. Yeah, so that's called converge. So right here, we are given the number of iteration, the learning rate alpha, and x prep, y true, and theta. Then history is to keep our data and our cost at the middle of the computation, because later we want to plot the cost function. Ignore this first. Yeah, then let's do this. So in the first iteration, we want to predict first. How do we predict? So just now we return a function called predict, right? And then we need x prep. And we also need theta. So x prep we are given here, and then theta we are also given here. All right, and then the cost. So after we make the prediction, we want to compute the cost first. Yeah, why do we need all this? Why do we want to do this in every iteration? Because the gradient of it need this. We want to have the prediction, and then yeah, we need to have the prediction. All right, so now let's compute the cost. This is the function that we returned just now. So y true. All right, y predict. It's given here. Oh no, y predict is here. Okay, yeah. And then this one is to save the thing and print the iteration, the cost at certain iteration. So I pre-return this. It's just like if our number of iteration is less than 10,000, then I'm going to print this 10 iteration once per 10 iteration. And if my number of iteration is more than 10,000, I'm going to print this once per 1,000 iteration. Yeah, so you can ignore this. So gradient, how to compute the gradient? So what's the name of the function again? Gradient, wait, cost gradient, okay. Cost gradient. And then we need y predict. Yeah, as given, as we have calculated just now. And then y true. Y true. And then finally x prep equal to x prep. Actually, in Python, we can also do this instead. You know, it's the same thing, but just now I did that because so that I know that, oh, this is going to assign to this y true in the function. Yeah, so it's the same. After computing the gradient, let's update it. So it's the crucial part of this function. So theta equal to theta minus the learning rate alpha times normal multiplication, yeah, this times the gradient. All right, so let's run this. So later we are going to iterate this a number of times. Yeah. So let's move on. Is everybody done with this? So I think it is now 9:55 and we can cover a little bit of it only, and I will move on faster. All right, so hope you can catch it. So here the visualize prediction function, I already written it because I don't think this is necessary for this workshop. Just run this, later we'll use it. And then visualize the cost function is the, the convex plot of the cost function. Also run this. So here we want to use our linear regression to make prediction on the data set. So data set with one feature, let's get it back. So it's called x1d and y1d, right? So x1d, yeah, it's still there. x1d dot shape. All right, and then y1d dot shape. So we are going to do that now. So visualize it again. So we are going to do a prediction right here. So what are the number of features? So where can we get from? So I think I can just write 1 because I know that my number of features is 1. And then x1d prep is going to be concat x0 to our x1d. All right, and then theta, we are going to randomly initialize it using this. So the shape of it is n1d plus 1 by 1. So this is randomly initialized. Yeah. So we assign a seed here because I want you to get the same value with me. Let's see the data. Data 1D. Yeah, so it's right here. So let's do the gradient descent. Let's start training our model. So we are going to learn a new data, and I call it data new and history 1D. History 1D is to keep the cost and data as I mentioned just now. So gradient descent, I'm going to need number of iterations. Let's say 100. And then learning rate. Let's say 0.1. And then x prep is my x1d prep. And then y true is my y1d. Data is going to be my data 1d as specified here. So let's run this. Oh, what's wrong? We can see that. So the cost is keep on increasing until it finally explode it out of the size of the the integer. So what can we do about it? So it's probably the function, this gradient descent has already overshoot the cost function. So let's put a smaller learning rate, 0.01. Oh, it's overshoot again. Let's try this. Oh, kind of overshoot because the cost is keep on increasing. Oh, finally, it is finally decreasing. So let's run it more. 10,000 iteration. Yeah, so we can see that the cost is decreasing. Then let's plot the learning curve. This thing is called learning curve. So the cost and the iteration. So we can see that our cost is actually decreasing. And then we make a prediction right here. So how to make the prediction? So predict. So we want to visualize, plot prediction, sorry. So I think I'm going to summarize after this. X1D prep, and then this one is Y1D. This one is data 1D. And then this one is number of dimension is 1. This I plot using the old data, and this I plot using the new data. Okay, so what's wrong? Yeah, I didn't specify that. So data and data. Oh, what's wrong with this? So it's 1D prep. So it is not converged yet. So probably we need to run more. Yeah, I think it's converged. Let's plot it again. So it's still running, as we can see. All right, so I think it's finally converged. Yeah, so here's our new prediction. And let's visualize the cost. I think this is the last one. X is equal to x1d prep, then y is equal to y true. And then history is a thing that we take note during the gradient descent. History 1d. And yeah, let's see this. Y true is not defined. Oh, it's called y1d, sorry. 1d. So yeah, here's our gradient, our cost function plot. And just now from epoch 1, the first iteration until here, we kind of come to a minimum. So it's very slow, as you can see. So yeah, I will skip it here. And then dataset with 2 feature is also similar, but it's just on the 2D data. And then sorry to inform that I have to delay another 5 minutes to say about a little bit about this. So as we can see, so our x1d, the value is very large, right? Let's see the max. So the max is this, then the mean is this. So the value is a lot, you know, very large and small. And then the cost function, the plot of the cost function will looks like this. So this is called a contour plot. So you can imagine this, the 3D plot, but you know, the shape is elongated. And if we scaled it to a range of, for example, -1 to 1, then the cost function will look like this. So if that's the case, then our gradient descent can perform faster. So here's the way to do the scaling. That's two-way, normalization and standardization. So I think I need to end the session here. Sorry for the time delay. All right, before that, so until here, anybody have any problem with it? So if no, I will just briefly say about it. So just now, if you scale the data, you see our x2 is right here, you know, very sparse from 0 to 2500. And then if you scaled it, you know, you see the range. And then we scaled it and finally trained it. You see we can done it on 200 iteration. And the prediction is pretty good. So scaling data is very important in machine learning. Yeah. And then we can't cover the underfitting and overfitting here, but you can have a look later using the notebook I will send to you. All right, and then we have an exercise on the real world data set, but they have cleaned it. So the data set is going to be, you know, scaled, and then we just need to run it. All right, and then we also can try the model from Scikit-Learn and directly access it. Yeah, so sorry to delay the time. And yeah, the key takeaway of this workshop is that gradient descent is very important. And then the common term in ML. So all this term is, you know, can be used in deep learning or whatever. It's all commonly appear in the context of ML. Yeah, scaling is like normalization. Okay, so feature scaling can increase the training speed, and Vectorization makes things easier. As you can see from just now, I implement the gradient part. I take a lot of time to implement it. Yeah, so that's all. That's all the coding session. Later, I'll send you the complete version. So sorry for that. So later on, you can refer to this if you want to practice on it. Okay. Yeah, thank you very much. And let me share another screen. I think I'm sharing the same screen. All right, so you can access all the code and the slide in this GitHub repo. I send it to the chat. And then, yeah, later leave your feedback here. We'll give a form here. And is there any question do you want to ask us before we end this session, before we take our group photo? So I hope that you guys can understand the thing that I said just now. So the important part of this workshop is just to understand, linear regression, and it's very crucial for us to understand more about the other algorithm in machine learning. So yeah, thank you so much, everybody, and we'll take the group photo right now. Jimin, so everybody, if possible, try to turn on your camera. So Jimin, can you help me to take the photo later? Yeah.
Yeah, sure.
Sorry, guys. Yeah, so are we ready to take a photo right now? So
yes, I'm ready. Yeah.
Yeah. Jinping, remember to count down when you want to take a photo.
All right, sure. Yeah. Should I start counting now, or
I
wait
think
for a while?
yes. I think yes.
All right. So 3, 2, 1. Okay, another one. 3, 2, 1.
Let's take one picture with this sign, the GDSC logo. Yeah. All right.
Hold on. All right. So 3, 2, 1.
Yeah.
Okay.
So
Yeah, I think it's fine.
thank you guys. So I hope you all can fill in the feedback form so that we can know what to improve later on. And then you can access to your GitHub repo for the complete code. And if you want to know more about it, refer to the proof, refer to the Jupyter notebook for the, for the code. So I think it's very beneficial for you all to, visualize the cost function. Yeah, you can do it later. Yeah, so thank you so much, everybody. That's all for our first session, and second session will be on Python. So we'll cover about NumPy, pandas, and matplotlib. Yeah. So thank you very much, guys. Yeah, so Junbing, let's go.
All right, sure.